Can you all hear me? Yeah, you can hear me now. Cool. Welcome. We're going to talk about some lower level C# than we might be used to, but we're going to try to avoid using the unsafe keyword. So what happened is I was porting a project that was originally written in C to C#. And if you want to port such a project, it really helps to understand what it is that you're porting. If you were actively involved in writing that original project, it should have been probably a lot easier. So let's briefly show some more information about the original project that we were porting. So I ported Doom from 1992 from C to C#. But unfortunately, when id Software started creating Doom, I was only 10 years old, so I was not actively involved in the project. However, I do have some hands-on experience with what the project is supposed to be doing, namely shooting demons. I'm pretty good at that. And there's also a lot of information available out there. There's a bunch of wikis. There are even books available about the entire game engine. So there's a lot of information that we can use. And of course, Doom source code is freely available, which is a ton of information right there. It's also pretty well structured. So I was able to port this code base very modularly as well. Now, before I show the port in a brief history, let me quickly introduce myself. Hi, I am Wesley. I'm a consultant at Xebia in Belgium. I call myself a coding architect because I don't like to live in an ivory tower. Also a coffee enthusiast, a beer aficionado, and I have some crazy side projects like this one. And you can find my socials using that QR code, but you'll get the slides at the end as well. So back in the summer of 2022, which is when we typically get summer vacation, in August for us, that is, I started working on this port. And about a week later after starting, I got my first output. So I got the title screen up and running from Doom. And then I started adding more and more functionality. I started first implementing the menu logic and adding more functionality to the port. Of course, I needed to render some levels. So a few days later, I got the rendering mostly working. As you can see here, this is this is map 5 of the first episode in the shareware version. This is actually the demo that's about to play. So whenever you start Doom, if you don't know Doom, it starts playing the demos until you start playing the game. But as you can see, we were still missing some parts. We were missing the status bar below. So a day later, I added a status bar, which shows the amount of ammo you have left, the health, the armor, and so on. For now, nothing really happened any beyond the point that it shows you the demo, because there was no input handling yet. So it did read the demo contents, and it tried to play the demo contents, but there was nothing handling the demo contents yet. So again, a few days later, I added the input handling and could translate whatever the demo was doing into actually playing those actions again on the screen. I also had a little problem that I like to call the pogo stick incident. So if you were just looking around, that worked just fine. But the moment that you start running forward, well, something interesting happened. You started bouncing around like crazy. Turns out geometry is pretty hard to implement, even if you were doing a port. A few days later, I got those bugs fixed, including the rendering bugs that were apparent. So it started to looking already a little bit more like a game. You could actually also pick up some of the items. You could interact with some of the elements in the game, but I did not implement everything yet. And then I had to start working again because it was already September. By the end of September, I got like, let's say 80% of the game and the port finished. I could start playing this, but if you would hear this, it will also play sound and music, but the sound and music support was only added way later. Now, talking about the port, there are a few things that I came across while porting the original C source code. And of course, C contains a lot of pointers. And if you say pointers in C#, you say the unsafe keyword. But I didn't want to use the unsafe keyword. So this is why I'm going to talk about how I did the port without using it, but I also have to talk about what the unsafe keyword is. I also have to talk about memory management, because the way that Doom works, it has to deal with a lot of memory management. It has to deal with loading data from a binary file, because that's where it stores all the game data. And then it does some really crazy stuff with functions and reference pointers. So let's start with the unsafe keywords. When we write C# code, most of our code is going to be verifiably safe, which means that the compiler and the jitter can verify that the code that we're writing is doing safe things. We're not going to directly access memory in some weird addresses using pointers, or we're going to allocate memory by itself. We're just very nicely creating arrays, objects, structs in managed memory. So the garbage collector will be able to do its job and clean everything up for us. However, we can use that unsafe keyword to add contexts to say this block of code is going to be potentially unsafe, or this method, this function, to even full types being unsafe. And within those unsafe contexts, we can provide memory access directly by using pointers. We can allocate in free memory, as free as we want, and then live outside the garbage collector and be smarter than the garbage collector. Now, on the right side, you can see some sample code. This is borrowed from the documentation side from C#. And this code does nothing more than traverse an array and manipulate it in a more direct way using pointers. Let me zoom in a little bit on the code. I removed all of the comments because we don't need comments. And let's see what it does. So first of all, we have to mark the part where we're going to introduce pointers as being unsafe, because we're using pointers. And then we're going to create a pointer called P, which references the first element in the array A. So it's pointing to 10. That's all it's doing. Now, we want to fix that pointer to the heap so that we are not moving that pointer around. It's going to stay pointing to that first element in the array, which is why we do the fix thing. And then inside that fixed block, we can start creating another pointer called P2, and it gets the same address as the pointer P. So we have two pointers now pointing to the first element. And then we can do a console.write line. And here we're not writing the address of P2, but we're dereferencing the pointer and getting the value that it's pointing to, and then writing that to the console. So here we're outputting the number 10. Then we can increase our pointer by 1. And C# is smart enough to say this is not 1 byte further in address space, but it's actually 4 bytes further in address space, because we're dealing with ints, and ints in C# are 4 bytes long. So we're moving our pointer basically to the second index in our array, and we're pointing now to the number 20. Below, we're doing something different. We're using that original pointer that points to the first array item, and instead of changing the address, we're now changing the value that the address is pointing to. So we're dereferencing P, adding 1, and our console.write line will now print 11 instead of 10. Now, using unsafe, that doesn't necessarily mean that the code that you're going to write in an unsafe context is not safe. It just means that there's no way for the compiler or the jitter to automatically verify that you're writing safe or unsafe code. It just means, here be dragons. So why It's why should you use unsafe? Just to use the pointers, but to make my point more clear, pun intended, let's verify that same unsafe code as before with the safe version next to it. This is what we would write every day. We just create an index, which is an int in this case, automatically inferred. And we can create an index 2, which is a copy of the index, directly go into the array, using that index, increasing the index, and so on. It's exactly the same thing. Why make it hard on ourselves? So typically, the answer would be performance. Okay, let's benchmark. But before I benchmark, let me quickly show what is being generated behind the scenes. So if I jump over to the intermediate language, is this readable for everyone? All right, cool. This is the unsafe version. And as you can see, let's go to this line. It will put something on the stack, which is the pointer, and then indirectly loads an int32 from the specified address on the stack. So basically saying, I have a pointer, it points to something that should be an int. I'm loading that int so that I can call system console with that int. It uses the pointer. So when you go to the safe version and you start looking at when you go to an array, here it just loads elements from an array. So this is not using pointers in IL. However, when you start changing elements inside of an array, you're loading the address of the array element and also indirectly loading from that address. So you're still using pointers here. It's just hidden away from you. So whenever you're doing safe C# code, there might still be pointers generated for you behind the scenes. So that might already give you an indication of the performance issues. So let's see. If I run both the unsafe and the safe versions against, I ran them against .NET 6, 7, and 8. I also used ahead of time compilation in both cases. And you see the performance here is almost on par. It's, you could say this is margin of error in between. And why is it the case? Because, as I said, the IL for the safe versions also uses pointers in some places. It just means that it's abstracted away from you. I'm not saying here that unsafe C# code is never going to be more performant, because it can disable like array out-of-bound checks for you. But in most cases, for us, mere mortals, it will not necessarily mean that it's going to be more performant. If you're going to use unsafe all the time, you might get more headaches though. So your mileage may vary. Now, when moving on in the porting of Doom, I also have to talk about how Doom manages its memory. Because, of course, it's a C program. And if you open a C program, you're going to encounter those pointers, those asterisks, those ampersands all over the place. And you're also going to come across memory allocation functions like the malloc method, calloc, realloc, the free one to release memory again, or if you're inside a C++ project, you can also encounter the new and the delete keywords. And unlike in a managed environment like .NET, C and C++, they don't use a garbage collector. So whenever you allocate memory, you also have the responsibility to free it again. If you allocate a handle to a file or a network port, you have to free that again as well. Just like we should dispose everything and sometimes forget or dispose it too quickly or to a like HTTP client, there's like some caveats, but you need to be aware of what you're doing more in C and C++ and C# is a little bit more forgiving. Now, there are some cases where you can also opt in to use a garbage collector in C++. You can do C++ in Visual Studio with .NET and manage memory as well. But let's assume, especially in the case of Doom, that there was no garbage collector available. And let's give an example as well, how classic C may do things. And just as in C#, you can still create an array. You can say, hey, I want a name that can be 100 characters in size. And yeah, that works. If you know during writing of the code that you're only going to need 100 characters, works just fine. But let's say that you were passed on a name length, and then you say, I can create a pointer to a name 2, and then allocate using the malloc method, name length times the size of one character. And then you have space enough to allocate exactly that name. And then you can try to string copy, and this is already a bad example, because string copy in this case does not verify that you're going to go out of bounds of your memory. There's another method for that. But this is the older C variants. They didn't have strncopy in that day. Now, malloc is also going to return you a void star, which is a special kind of pointer. It's a pointer to anything you want, which also means that you can do some weird stuff. You can say, hey, I have this name2 pointer thingy, and even though I typed it as a character pointer here, I can just change its address. I'm going to add 3 to that pointer, dereference it, cast it to an int, or I could even cast it to an int pointer if I wanted to, and then change how it's addressing, and then try to read it. And it will work, as long as I don't go out of bounds, because then I get an access violation exception. But I can do this, and it might be something weird, but this is actually being used a lot in C code to immediately jump inside of complex structures to correct fields inside of them, to speed up the process. And of course, don't forget to free the memory if you're done using it. Moving on to C++. There you can create new persons and delete persons, and then you can, this is because they introduce classes, concepts in C++, and then you can very easily just allocate the memory, get a type pointer back for person, and you don't need to size off the person anymore. It will know how big a person is. That's a lot easier. Talking about Doom, whenever Doom starts, it needs to allocate a bunch of memory for the game to work. And in this case, that works by allocating a main zone of memory on the heap, calling the izone base method. And the izone base method is just using malloc to allocate 6 megabytes of memory space. This is, by the way, it used to be 4, but this code version also supports Doom 2, which increased the memory usage by 2 megabytes. So now we have a huge chunk of memory that we can use to load all of our data in. And to do this, id Software created another method called zone memory allocation, zmalloc, to say, hey, I'm loading a level, and part of my level is the vertices where all of the lines will go. And I need now enough memory in that zone for number of vertices times the size of one vertex. And then it will look in that big chunk of memory. If there's enough space available, then it will allocate that space for you. It will tag it, in this case, with the PU level tag, which means whenever it's going to do a zone free call, it can immediately free up all of the level data when you're switching between levels. It's actually a very smart garbage collector for Doom, you might say. And when this code was written back in 1992, this level of memory management really was necessary for Doom to perform well on the hardware that was available. It's also more performant than doing this rather than doing malloc and free all the time, because now they just had a big chunk. They could free up chunks of memory. They could, just like you could defrag your old hard drive, they could fragment all of the memory that was allocated back together. And then they didn't have to bother releasing memory and allocating memory all the time. Also because what if some other process on the PC was going to run away with that memory? Your game would crash. That's not what you want. Now, moving to C#, I was not going to bother implementing all of that zone memory allocation thing. We have a garbage collector. I've got 64 gigs of memory in my machine. And even if I had only 8 gigs of memory, Doom is only going to use 6. So why bother? I mean, it's already hard enough to port C to C#. I'm not going to bother porting a memory allocation thing. So I just made the decision to use classes wherever I thought it was appropriate to use classes, use structs where I think maybe this is more suitable for a struct, and then use arrays rather than using lists, because I don't need all of the special functions that a list offers me. I just need an array, and in most cases, it's pre-allocated. So I know I'm always going to have, for example, that many bytes in my screen buffer is going to be immediately that size all the time. In this case, my vertices will be different per level. So I pre-allocate my vertices with an empty array. And then whenever I load my actual vertices, I will just say, hey, I need a new array of that times vertices. Now, I did mention lists of T and T arrays. Let's do another benchmark. Because I was going in this port and I just immediately decided I'm going to go for arrays, because arrays are fast. There's no denying this. But then someone called me out and said, you could just have pre-allocated your list of T. You could have a list of bytes, and if you know num vertices, you can say new list of T, num vertices, you're done. I said, you're not wrong. So let's find out what's the fastest way. But then I was like, it's going to be easy to just say pre-allocated array versus pre-allocated list. What if I am stupid and just say, I'm going to do new list and see what happens? Or I can also say, what if I come up with my own ways to resize my arrays and use array copy or array.resize? So that's what I did. I compared the pre-allocated array with pre-allocated list to dynamically resized list. And then I implemented 3 versions of dynamically resized arrays. The first one mimics what the list is doing. So it starts with 4 items and then it doubles in size every time. The chunked resized is going to just start with 10 and then increases by 10. So it's the stupid resized version. And aggressively resizing just means increase by 1 every time. I ran the benchmark again against .NET 6, 7, and 8. I'm only showing the results for .NET 8 because, again, the differences were not that great between the different versions, but also I would need a screen that goes a little bit further than this. All of the results are in the slide deck, and you can get the slide deck afterwards. And it should not be a surprise to see that a pre-allocated array is going to be the fastest of all of them. So it only takes for this benchmark 6.7 microseconds to run that workload. But list of T pre-allocated, I mean, that difference to me is small enough to say it's a good viable solution. And if you want to use lists, go ahead. In this case, it's an old game. It doesn't need that many performance. It's It's not that it's going to be hurting your gamer's experience in this case. Moving to the dynamically algorithms, I was actually not that surprised to see that the list version was also very performant. It's a bit slower, let's say 1 microsecond slower, and microseconds in this case, again, it's not that much. But it clearly shows that the algorithm that was chosen here is a good alternative. Of course, it can be a little bit more allocatey because you see it's immediately doubled in size from 4 to 8 kilobytes. But still, good solution. And of course, because it's the same algorithm, you see that the resize doubling sequence array version is within the same ballpark as the list version. Although, because it's an array, it has less overhead, it's still faster and a little less allocating. And then you can also see that my other 2 attempts just immediately go out through the roof, adding 10 microseconds for the chunked one and almost going up to 100 microseconds for the aggressively resized one. And yeah, let's not talk about how many bytes it's being allocating, because it's even using array.resize. I'm not doing this myself, so it's using the smart way, but in a very inefficient way. All right, so we have memory management done. Let's load data from Doom. So whenever we read binary data in Doom, there's this big file that we have to open called the WAD file. WAD stands for where's all the data. And it contains, well, like any old typical file format, it contains a file header indicating what the file is for. And then it contains a table of contents to say, if you want to locate a certain chunk of data that you need, this is where you're going to find that. And then it also, of course, contains all of the file lumps containing the game data. And whenever it starts the game, it calls a function W for all of the WAD functions, .add file. And it's going to, well, if you open and read a file in C, it's pretty similar as what we're doing in C#. So you're opening a file handle, you're giving it the file name that you want to open. You're going to specify your intentions. In this case, we only need read-only access to that file, and we're going to read it in binary mode. And then if that file can be opened, you get a valid handle back. You can start reading from that handle. And in this case, we are reading the size of the header structure inside the header variable so that we can read our WAD header contents. This is the C version. If we port that to C#, you get, it's a bit different, but we're still opening a file handle. In this case, it's called a file stream. We're still saying, hey, I need read access to that file. I'm a bit egocentric. I'm not going to share that file handle. I want this file to be for myself. I don't want anyone else to access the game file that I'm loading. And then the binary mode here is interpreted by calling a binary reader to that file stream. And because I already knew that inside the WAD file, if we encounter character data, it's going to be in ASCII encoding. I'm giving it the ASCII encoding immediately. And I'm also saying, hey, whenever I close that binary reader, you can also go ahead and close that file stream for me. So that's the equivalent of freeing my file handle as well. And then when we are reading that header, I could have used like these Marshall methods to say, hey, I have this struct called a WAD info. Go ahead and read from that file and marshal it into that struct. Or I can just go ahead and say, hey, I'm going to read 4 bytes from you at the first position, and then use the ASCII encoding to interpret those 4 bytes into ASCII characters. And then I know that this first 4 bytes, they need to be either IWAD or PWAD.
So IWAT means it's an internal /core WAT file, which is the Doom game itself. And a PWAT is a patch WAT. So Doom already supported modding, so you could mod the game if you wanted to. And then the next 2 bytes from the WAT info file. In this case, I'm just using the read int32 method from the binary reader to say, hey, I'm going to read an integer, which is, the first one is how many data lumps are there in the WAT file, and the second one is where is the directory of all the WATs being stored in the file. So I can immediately jump to the table of contents and then see where all of the WAT files, all of the lumps are. Speaking about a lump has a integer value, which is where in this WAT file is the data being stored for that lump. So this is just your file entry in the file system of Doom. So this is saying, hey, I have a file called doomguy.texture. I'm making this up right now, but that could be one of them. And then the file is located here in the WAT file, and then it's going to be that many bytes long. And then you get a picture. Maybe you get the Doom logo picture. Now, if we want to read these data structures from Doom, we must ask ourselves 2 questions. Well, it's a bunch of more questions, but if we want to read something, the first question is going to be, what's the actual size of this thing? How many bytes is a character? You could say it's going to be 1, but even in C++, at some point, you had like, I don't know, 5 or 6 different types of characters. You had like LB strings and WCHAR and Unicode, and I don't know what a char is. And an int, how many bytes is an int? We're thinking it's 4. It has been 2 as well. So it all depends on both the system that you're working in, but also how it's being stored in that file. Because they might say an int is 4 bytes on the compiler level, but in the binary file, it might have been stored as 2 bytes just to conserve the data, because they knew they were never going to go across the boundary of 32,768. In this case, the file lump is going to be 16 bytes long. So our ints are 4 bytes times 2, and then 8 characters being 1 byte, all of them. So that's our first set of questions, data sizing. The next question that we need to answer is, how are these multi-byte values being stored? What's the endianness? If we look at the value for a 3B to C1D in hex, it can be stored in multiple different ways. You could have it stored in big endian mode, where the most significant byte goes first. And then if you have a hex dump of that value, you would see the same order as it appears here. And you could have little endian modes. So then the least significant byte goes first, and then you see it being turned around, and then your 4A 3B to C1D becomes 1D to C3B 4A. And then there is also another system. I didn't know this before I started creating my slides even. There's a middle endian as well, which treats, if you have like data that's more than 8 bytes, so you have words of 16 bits, it could swap those around and then keeping the order of the 8 bits, or it could keep the order and swap those around. I don't know how they created programs for this system, but apparently the PDP-11 used this. Now, luckily, sometimes a monopoly is a good thing, and most of our systems these days are based on the Intel 8 x86, which means that most of our systems are going to be little endian. And if you use binary reader and you say read in 32, it's going to read in little endian. However, if you're going to port C to C#, still look at the documentation, still look at the raw data that you're going to read in binary form,
because even though Doom uses little endian, one of the ports for the Atari Jaguar used big endian instead, because the system was big endian. So just still keep that in mind. Right, so memory management done. We're reading our binary data. Let's implement our Doom code. And for that, we're going to start messing about with function pointers. If I look back at my status bar here, that code was actually a piece of beauty. They already used widgets for this. So the status bar contains different widgets, and then you have the ammo widget, which is a number widget. You have the health widget, which is a percentage widget that inherits from number widget because it already knows how to represent numbers, and then just adds a percentage after that. So this was already object-oriented code way ahead of its time. And looking at the original C code for creating that health percentage, you call a method called stlib_init%. You're going to store that in the health variable. You give it the X and the Y positions where it should be shown in the status bar. You give it a list of the digits. You give it the player's health. You give it the fact if it needs to be showed or not. And then you give it that percentage sign. But the special thing here is you're not giving it the player's health, because then it would be 100% all the time. You're giving it a reference to the player's health. So whenever you're reading and updating the status bar, it could reflect the actual value at that time. So whenever you get hit, you would see that immediately whenever the status bar tick hits for the update. And if you pick up a health file, you'll see it increase again. How am I going to port this? Because I don't want to use pointers. Well, junior me would say, hey, I'm smart. I know this thing called by reference. So I'll just do this and say, hey, in my percentage widget, when I construct it, I'm going to give a reference to the int number, and then boom, I'm done. Well, not exactly, right? Because what happens here is you're indeed passing the reference to the number, and then inside of that constructor, you get access to the number argument. You can store the value from number in the property number. And you could have changed that number, and then the caller of this constructor would have received the updated value. But you're not storing the reference to that number here. You're just getting access to that reference, just for a little while. And whenever you're going out of the scope of the constructor, the reference is gone again. This is the safe version of a pointer. So a few years later, I might have started thinking, right, that doesn't work. This works. I'm going to box it inside of a class. I'm going to create a reference thing, and I can even do smart stuff. I can use generics and say, hey, I'm going to create a reference to T, and then I can store the value in there. And then I have, whenever I use the same reference of the object, it's going to reference all of the same values, and I can read the value at runtime and done. Yeah, that works. But is it elegant? Some might say yes. Well, in this case, there's a smarter way to approach this as well. Now, I must be honest, this is very close to what the intentional code would have been. Because in the original code, the C code, you're giving the reference. So nothing would hold you back to also increase the value or change the value whenever you're doing the status bar updates. Because you have full access to that memory space. Here as well. And this is one of the few places where I actually diverged from the port, because I want to keep the port as close to the original C code as possible. I even kept some of the bugs inside. And I can tell you later why. So another way to do this is just give it a func.
give it a func of int instead, and then we can use a lambda function to say, hey, whenever you need to have that updated value, here's how you can get it. And that looks like this. So when you create your percentage widget, the rest is all the same code, but instead of referencing that player's health, you're just saying, hey, whenever you need player's health, go to the underscore player.health, and then boom, you got your health. And if you look at this code, it's not actually that different from the original C code. So I was very happy with this solution. All right. Now, of course, there's still not a lot happening in our game. We have a status bar, but there's nothing reacting yet. So Doom has a thing called thinkers and map objects. And thinkers are things that react in a level. So if you approach a door, you can open a door. And some doors can even be opened by enemies. If they hear you, they can open the door and start chasing you. There's special ceilings that start going down whenever you enter a room so that you are forced to escape the room. And there are floors that suddenly become staircases. And map objects are special thinkers. These are most of the times the enemies that start chasing you, but you, the player yourself, are also a map object. And these things get whenever they're supposed to act in the game, they're going to be assigned the map object thinker method in the original source code so that they can start reacting to the level. Now, how does this work in the original source code? You have a doubly linked list of actors, and every actor has a function of type action f underscore t. And that's a union. And a union means it can be anything within that union. So that action could be a simple method with no parameters. It could be a method with one void star parameter, and void star means anything you want. Or it could be a method with two void star parameters, even worse, two things that can be anything they want. How am I going to port this to C#? Because I don't want to use objects. I want to be a little bit more type safe, because this is basically object, right? Void star for us is an object. So what I did is I kept the concept of the thinker, and I could have gone the same way. I could have said, look, I can have an action with nothing. I could have an action with one something, and I couldn't have an action with two somethings, and then find all of the places in the code base where it could be that kind of a thinker or that kind of a map object. But that would have meant that I had a thinker with maybe 30, 40 action types, and I was not willing to implement that much different types. I wanted to be a little bit smarter than that. Also because a thinker gets assigned a method. A thinker also gets unassigned that method. It gets set to nothing, to say this thinker is no longer doing anything. It should get disposed. It should maybe become idle and wait until something happens, and then it gets assigned a function again. If I have 40 action types, I need to do that 40 times and keep track of which ones I need to set. So instead, I just used a single action delegate with an action params, and action params can be any kind of thing that I want it to be. Like, for example, it could be a map object. I'm running ahead of myself here. Action params, I actually looked at the source code and looked at all of the places where these actions were being used, and then identified the 4 different types that it can be. So one of them would be the map object. One of them would be the player itself. Another one was special, was the player sprite. And that's basically when you're playing the game, you see the status bar, and then just above it, you see the weapon that you're holding. That's the player sprite. And if you have, for example,
the shotgun and you need to reload, you'll see that reload movement. And then that's the action that's happening. Or it could be any kind of thinker, the door, the ceiling, the floor, whatever. And then whenever you call one of those methods that you assign to the action, within that method, it's very easy to see, well, I'm expecting a thinker here, not a map object nor a player. And if that thinker is not a door, then I don't do anything. And in case, I'm never actually going to hit that point anyway, but this is just me being type safe, because this method is only going to be called in cases where the action params contains a thinker and the thinker is a door, but just to be type safe. And then whenever you enter this method, you can then open or close the door as you need to. All right. So now we have all of our things implemented. That's cool. I do have one more thing, however. I don't know who was here during Scott Hanselman's talk yesterday. A few people. He told us that open source projects, if I recall correctly, are not cool if they don't have ASCII art. So let's see if I go to my Visual Studio. I must warn you, if you're triggered by flashing screens, if you have epilepsy, look away. I will tell you when you can look again. But I can run Doom using ASCII in a console. It's not that performant as the normal version, but it works. And the way that this works is by the lovely NuGet package Spectre console. So if you want to do special ASCII art or special stuff in consoles, do look at Spectre console. It's an amazing NuGet package. I recommend it to everyone if they do a CLI. But that works. Of course, you also have the more normal Windows version of the game. If you can start looking again, it's less flashy now. But yeah, that works too. And I did also render the console output that you get initially when you start the game. So that works as well. And I can start playing Doom if I want to. I can start running around. And of course, this being C#, it also supports MAUI. We have it running on Android as well. And Avalonia is also in the works. So we can run this on a Mac now without a lot of effort. So that's cool. Now, to summarize what I try to convey today, first and foremost, unsafe code isn't necessarily unsafe per se, but also isn't necessarily more performant. It just gives you a lot of extras if you want to have like direct memory access, but with great power comes great responsibility, of course. It's actually quite easy to translate C code into modern C#. However, C++, that's a whole different story. Especially, I mean, you can write C++ and just have a C program, of course, but whenever you go and have like C++ with all the defines and the macros, that's going to be already interesting in some places. And if you use, if you have classes that use multiple inheritance, that's also a bit of a problem. But also C++ is generic type, because if I recall correctly, in C++ you can, for example, say, hey, I have this list of int, just like you would in C#. But you could also say, I have this list of int, which is going to be 5 ints long. And then it will optimize for 5 ints in some way. That's really magic for me. But I think behind the scenes, there's like a version that says, hey, if you're going to create a a vector of ints that's going to be only this size, then just immediately create 5 ints as fields and use those instead of creating an array of ints instead. So there's like trickery going on. And if you want to translate that, it's going to be a lot more work. And then of course, if you encounter void star, that should be a uh-oh moment, and then you need to inspect what's really going on here. Is this just a way to directly go into a specific area of my structures, or is this actually a method pointer? What do I need to do? And whenever you come across a method pointer, try to fix things with actions and functions, because that's the easy way to deal with them. You could also use delegate stars in unsafe code, but that's a whole different level. And that's basically it. So if you have any questions, I will take them now. You can also already access the slide deck if you want to using that QR code. And if there are no questions, then I have one more thing to say. I have stickers with the Doom Sharp logo. I have a crazy artist who created them for me. So if you want a sticker, you can find me here or find me outside later. And then in a few moments, there also will be a certain person called Lars who will be doing the party introduction. And I suppose there will be beers as well. So I'm not sure if there already are beers outside, but I might give you early access to beers, which is always nice. Okay, any questions? No questions? Everything was clear. Start porting Doom then, right now. Or just take my source code. That works too. Right, cool. Thanks for listening.